now we finally move to lecture 18. When I say finally, is because this is where we introduce the third law of thermodynamics. So we have learned quite a bit so far. And along the way, we have introduced the entropy, and we've tried to treat it as formally and abstractly as possible while trying to understand where it's coming from. Of course, you have to realize that people who started looking at entropy many decades ago did not have this interpretation that we have now about microstate. And also there were a number of issues that were still left. So entropy seemed to be indeed a function of state. We've seen it a number of times, and on top of that, any physical process would yield increase in entropy, and in fact at equilibrium the entropy will be maximal. So that's what's very important. But one thing that people were struggling with is to exactly know what was the absolute value for entropy. Okay, and so that's the reason why it's so is because physically most of the processes we look at yield delta S, changes. There's some changes, delta U, delta S, things like that. So that means that you always have a relative information. And people were struggling a little bit with knowing what would be the entropy, what would be the value of the entropy, for example, what would be the reference value. So this is what we are going to do today, and this is what the third law is all about. So imagine that we want to measure entropy. Okay? Well, we already know a way to do this, because if you remember equations that we've seen quite a number of times, measuring entropy is doable through this reversible process related to the heat capacity. For example, at constant pressure. You can do the same at constant volume if you will. You just replace the P by V. And then what you do, you integrate that entropy, you integrate that value, and you get the value of the entropy. The problem is, again, is that integral is going to depend on the boundaries, T0 and T, right? Because it's a definite integral. So we still don't know what the entropy is at the lowest temperature. And that's a particular issue. So we know the entropy, the change in entropy, which is essentially the surface area that's shown there with an arrow on the plot on the right hand side, but we still don't know what's the reference of the entropy. So we know the changes, but we don't know exactly what it is as a reference. And this is what the third law of thermodynamics provides, and this is what we are going to discuss in the next few minutes. So let's go back into it. Let's go back to it. The third law, which is essentially due to work from Nernst and Planck, and we are going to see what's happening. And this is coming from looking at a reaction, and then we have seen that the change in the Gibbs function delta G was equal to delta H minus TdS. All right, it was all discussed in detail in the chapter on thermodynamic potential, and what we see when we look at this equation, what's interesting is that if temperature goes down, possibly to 0, we find that delta G is equal to delta H. So if we can measure both values, delta G and delta H, using different methods as we have seen before, we should see that delta G and delta H should get to the same point at 0 Kelvin. And they do. There is no issue with that. So the fact is they do get to the same value at t equals 0. However, there is something more. When this experiment is done, not only do they get the same value, but they do so asymptotically. So asymptotically means faster than the linear term. So imagine that delta S did not change with temperature. Okay, I mean, imagine that delta S is essentially does not care about the temperature particularly. Then the delta G and delta would converge into delta H linearly with temperature, right? As temperature goes down, you would get the delta H is equal to delta G. But it turns out experimentally it's done asymptotically. So somehow delta S also goes down with temperature. In fact, it goes down so that the entropy does no longer changes when you approach 0 Kelvin. So the fact that the entropy no longer changes when you get to the 0 Kelvin means that delta S tends to 0 for T tend to 0. And this is this experimental observation that led Nernst to make a statement of the third law of thermodynamics, which says that at near absolute 0, all reaction in a system in internal equilibrium take place with no change in entropy. So, in other words, when T goes to 0, delta S goes to 0. That's what it means. That particular definition has a number of key aspects to it, which is, for example, the internal equilibrium. So if you are not in an internal equilibrium, and I'm going to mention that again in a few seconds, if you're not in internal equilibrium, this is not true. This particular statement is not true. But let's consider first the internal equilibrium. So let's say that again. When the temperature goes to 0, the system no longer changes in entropy, no matter what happens. And so this led Planck to make a statement which is equivalent. And Planck said that when a system is in internal equilibrium again, so same constraint here, I mean same supposition, the entropy of that system is the same at absolute 0. So if you take any system that has internal equilibrium, the entropy is the same at absolute 0. And since it's the same, we can pick that reference to be 0. So in other words, what Planck says is that the entropy is 0 at 0 Kelvin. Okay? So that means that basically it gives you a scale to work with. It actually provides the origin of the scale to work with. So before, the second law of thermodynamics allowed us to calculate the change in entropy, but the third law tells you, well, you start at 0 Kelvin. So as I mentioned, the internal equilibrium words are very important. If you were, for example, looking into glassy material, glass is actually not in equilibrium, as you know. A glass is not in equilibrium. It means that it does not have a 0 entropy at 0 Kelvin. However, one thing that's important is that this definition is, of course, compatible with statistical mechanics. Remember that we said that from the Boltzmann tombstone that the entropy is proportional to the logarithm of the number of microstates. So presumably, if we are in an equilibrium situation at very low temperature, we should have the most stable situation, the ground state, which usually correspond to one single microstate, and the logarithm of 1 being 0, the entropy is 0. So this is one way to look at it, but we are going to see that in more detail in a few minutes. Now we can doubt the fact that the entropy is actually 0. Is it ever equal to 0? So let's try to consider an example just to tell you how there was a third definition, claim of the third law that was due to Simon, and actually it's probably a little more satisfactory, so that it takes into account all the scenarios. Let's introduce how we get there. Suppose you have n spinless atom in a perfect crystal. So the crystal is perfect. There is absolutely only one way to get the crystal in that shape. Remember, number of microstate, that's important. So clearly the entropy is 0. Okay, so the entropy is 0. But now, suppose that each nucleus has momentum I. Okay, and if the momentum is not trivially 0, then we know there are 2I plus 1 possible orientations for each nuclear spin. But if this is true, then that means that the entropy is not 0, of course, because we have the number of microstates is larger than 1. So what's wrong? Well, there is nothing wrong, really. The point is, when we consider the different variables, like now the nuclear spin, we have to consider all the interaction, even those that we usually neglect because they are so small. Why do we need to? Well, first of all, let me tell you, there is an interaction between nuclear spin because they correspond to magnetic moment, and according to the law of Biot-Savart, there is an associated magnetic field which therefore interact with the other spin. So there is an interaction. It's very small. It's actually extremely small. However, now we are actually dealing with extremely low temperature. So that means that we are starting to deal with temperature that are infinitesimally small, which means that if you look at the Boltzmann factor, for instance, even the tiniest of the interactions start to play a big role. It's kind of a scaling factor, if you will. In fact, that's what the real temperature is with the Boltzmann factor. So that means that in that case, the real ground state, as you decrease temperature really small, is for all the spin to be aligned. Let's say if it's in a ferromagnetic alignment. So in that case, if they are all aligned, there is indeed the entropy is indeed zero because you have only a spin, one microstate. But that's not even necessarily the case, right? Because suppose that we go down, we don't consider the nucleus anymore. We consider maybe the quarks or other subnuclear particle, or even further, things that we don't know. How do we know that corresponded to a one single microstate? How can we make so sure that the entropy is really zero? And in fact, this is almost a philosophical question, but the point is, each time we consider a different scale, and when I talk about scale, I'm talking about really the magnitude of the interactions. These interactions that usually you can neglect, you can no longer neglect when you get a temperature which is very, very close to zero. So this is an issue. However, we are lucky in our misery. We are lucky that the entropy is defined as a logarithm, and a logarithm of a number of microstates. And when we consider the different levels, as I mentioned now, first, let's say the electrons, now the nuclei, then the quarks, and so on and so forth, each time we consider those, the number of microstates is multiplied. So it actually increases with a multiplicative factor, which means because we have a logarithm in the entropy, the entropies are additive. So what we really mean is that the entropy of each aspect, for example, electron, nuclei, quarks, and so on and so forth, so the entropy of each aspect is indeed equal to zero. And if we were able to add all the interaction, even the tiniest one, okay, and this is where the imagination takes place here, where we are going into a physics that we don't necessarily understand yet, or we don't know anything about. But if we do that, we can add at the end, we add all these zero terms, and we get a real entropy of zero. This is the idea, okay? So this is all because we can do that because of the logarithm. And so those different interaction, those very weak interactions and subsystem, if you will, we call aspect. So Simon, the scientist, decided to call those subsystem as aspect. And he formulated the third law as follows. So it says that the contribution to the entropy of a system by each aspect of the system, which is in internal thermodynamic equilibrium, tends to zero as t goes to zero. So in other words, as t goes to zero, you see the different aspects, like for example the nuclear spin, the quark spin, and so on and so forth, all those going, the entropy contribution of each of them going to zero as temperature goes to zero. And so since the total entropy is the sum of the entropy of the increase in the number of microstates for each aspect, we are we are totally compatible with what we've done before. So now I'm going to spend the next few minutes talking to you about the consequences of the third law, and you might actually be amazed by the number of those consequences. This is pretty far-reaching. So the first one is related to heat capacities. Okay, so we remember the definition of heat capacity. We have C equal T ds over dt. Here there is no subscript V or P simply because it works in either case. Now we can do some simple calculus, differential calculus there, differential properties, and we find that this derivative is nothing else than the derivative, the change in entropy for a change in the logarithm of temperature. Now, if temperature goes to 0, the logarithm goes to minus infinity, and that means that if it goes to minus infinity and the entropy at the same time goes to 0, we just discussed this, right? This is the third law. Therefore, the heat capacity can only be equal to 0, right? So that's good. So that means that the heat capacity goes to 0. This result, of course, disagree with what we've done with the classical prediction that we've done for the ideal gas, and this is actually the key point that I'm going to make now, and I will make it again. The reason why it's supposed to be wrong is for the reason I just explained to you when I expressed the Simon's version of the third law. Okay, let's try to think about this. The ideal gas, we said there is no interaction between the particles. Clearly, this is a simplification. I mean, we do all understand this was a simplification. We were just amazed that it worked so well, so we kind of almost forgot that big simplification. But it's time to remember it. And in fact, at very low temperature, these interactions start to count, and think about the Boltzmann factor, if you will. And that is where the interaction, even though they are weak interaction, they start to matter quite a great deal. And in fact, this is the reason why the ideal gas law breaks down at very low temperature. For the good news is that at usual temperature, in everyday temperature, it works well, but at low temperature it does not. So we will revisit this later in this course. One other thing that I like to mention to you, which is extremely important here in my opinion, is the fact, what does it mean for the heat capacity goes to 0 when temperature goes to 0. So imagine that you are extremely close to 0 Kelvin. Imagine that you're at 0 Kelvin. We know that the heat capacity is 0. Heat capacity at 0 means that you need no energy added to the system to increase the temperature by 1 Kelvin. Right? This is the definition of the heat capacity. Heat capacity is the amount of energy you need to bring to the system to increase the temperature. But if the heat capacity is 0, that means that you essentially any tiniest amount would increase the temperature. So that might actually give you a hint why temperature can't really stay at 0, right? So maybe that gives you a hint right there. We'll discuss that in more detail in a second. Before that, let's have a look at the third law of thermodynamics, and it's a good and its effect on the thermal expansion. So this is a good way to remember a little bit how we treat those those different derivatives. Okay, let's try to do this patiently. So when the entropy goes to 0 as the temperature goes to 0, okay, again this is the third law. We have, for example, that this is related to the fact that we have ds over dp, it goes to 0, of course. So the change, this is essentially the Nernst version of the first law, right? There is no change in entropy when we close to t equals 0. But we can actually relate that equation, ds over dp at constant temperature at Maxwell relation, and here I'm actually going to click on this to get back to the slide where we introduced them. So this is the Maxwell relations, and ds over dp at constant temperature, this is the law right here, on the right hand side. So we are going to apply this, and then we end up with replacing this by this right here. And of course we can divide by the volume and so on and so forth, and then we'll remember what the isobaric expansivity, and again we click here, that isobaric expansivity was the change in volume as a function of temperature at given pressure. And of course it's the relative change, so we divide by the volume. Okay, nice. So we go back here. So basically what it means is that the isobaric expansivity, so how much the volume changes as a function of temperature at constant pressure, it's 0. So basically, if you had a system close to the 0 temperature, you would find that it will no longer expand or retract as a function of temperature close to the zero temperature. So that's an important consequence. It's a little bit harder to see exactly how this from an intuitive point of view. But okay, so now let's have a look at another consequence of the third law. And for example, we're talking about the ideal gas. We already discussed that the heat capacity was tending to zero. But in fact, we already know that Cp minus Cv is equal to R per mole for an ideal gas. And of course, as temperature goes to zero, the Cp and Cv tend to zero. So clearly, we cannot have that. But there is something else that's actually interesting too, because we calculated in the last lecture the entropy for an ideal gas as a function of temperature and volume, and it fails completely clearly because the logarithm diverges at t equals 0, it goes to minus infinity, even though it should be equal to 0. So it's another example that the ideal gas model does not work at low temperature, as I mentioned a few minutes ago, and this is because the weak interactions start to count, and it makes sense, of course, that they start to count at very low temperature because of how large they becomes compared to kBt. That's always the kind of the gauge, is kBt. And when t is almost 0, of course, that means that everything counts. Let's have a look at the third law. We discussed Curie's law in the last lecture quite a bit, so let's have a look at what happens with Curie's law. Curie's law says that the susceptibility goes as 1 over T, so basically explodes at low temperature. So we can calculate the change in entropy as a function of the magnetic field in an isothermal process. We can do that again using the different equations that we have seen before related to for example, the Maxwell relationship. And so what we found is that the entropy, what we see is that the entropy, the change in entropy is a function of magnetic field at constant temperature, should go to zero for low temperature. But the right hand side, it's not, because VB of course are just finite numbers, but we see that the derivative of chi with respect to t is actually, it diverges, right? It's an infinity. So in principle something is wrong here. So clearly the Curie's law, 1 over T for the susceptibility, breaks down at low temperature. And it does. At low temperature, it completely breaks down. And again, the reason why it breaks down is because Curie's law is purely related to independent magnetic moment. And one more time, the interaction there is between the magnetic moment, which we neglected, should not be neglected when you work at very low temperature. One more time. This is again the same story as we've seen before, but these things start to basically break down at very low temperature. And all of this can be gauged as by looking at how all those theory continuously lead to the right entropy at low temperature, and none of those theory were built for that. So clearly, most of them actually fail to do it. Okay, so this is again always gauging how far from if the interaction is strong or not at low temperature. If it's an interaction that's much smaller than kBt, then you can neglect it. For example, the interaction between nuclei, the magnetic interaction, is usually much smaller than kBt at room temperature, so you can neglect it. But that's certainly not the case of the interaction between electrons. At kBt, at room temperature, this is not negligible. Now, another thing that we discuss is the impossibility to attain zero. I already kind of gave you a clue about this, the fact that the heat capacity is goes to zero. That means that even if you reach zero, even 0 joule would increase the temperature, right? That's the idea. That's really what it means to have a heat capacity 0. But we can go back to the isothermal magnetization followed by adiabatic demagnetization that we've studied in the previous lecture. So you could think that why you could be able to do this. You should be able to do this. So you have different curves, a different magnetic field, as we have seen in the last lecture, and you could actually do an isothermal magnetization followed by adiabatic demagnetization, and so on and so forth. So we can keep doing that, and then if we do that, there is no geometrically there is no doubt you will end up going at 0 Kelvin. You will keep going down. You will keep decreasing the temperature. But this plot is incorrect. You can see directly that that plot is incorrect because that plot does not take into account the third law of thermodynamics. At least it does not for chi1, because we know that both chi1 and chi2 must end up at 0 Kelvin. So a more accurate plot is this one. And so the idea of doing this magnetization for, isothermal magnetization followed by adiabatic demagnetization again and again and again, you can see that you end up with an infinite series there. So you need to do it an infinitely large number of times in order for the point that's following this, for the state that follows those arrows to get actually to 0. So that means that you can only attain 0 with an infinite number of steps. That's basically what it says. Okay, so one last point I'd like to mention before we get to the summary slide. The Carnot engine, and we've discussed it, and you know that the efficiency eta is 1 minus TL over TH. And then when you just look at the equation, you say, well, if I can have the cold reservoir to be at 0 Kelvin, okay, if I can have this at 0 Kelvin, I would be all set. Okay, I could be all set. So because then the efficiency would be 100%. So the fact that we cannot attain 0 Kelvin, right? We just discussed that we cannot attain it, or at least we cannot certainly not stay there, but we cannot attain it either. Means that you could not actually create this. But some people say, well, then therefore, if the impossibility to attain 0 Kelvin is a consequence of the third law, it also shows it's also equivalent to saying that the efficiency cannot be 100%. So maybe this is just another version of the second law of thermodynamics. You know, one of the versions of the second law of thermodynamics was that the efficiency could not be 1. In other words, you cannot transform completely heat into work, right? So, but the reality is that it's a bit more complicated than this, because the point is that there is the issue to actually create the system at 0 Kelvin itself. Okay, it's not just its consequences. And in fact, if you were trying to do a Carnot engine with a reservoir, and remember the reservoir has to be able to absorb heat, right, in order to keep the same temperature. If you have a system at 0 temperature, any amount of heat would actually increase the temperature tremendously. So that you could not actually create a reservoir as we define it in thermodynamics using a 0 Kelvin. So the fact that you cannot even consider a reservoir is not a consequence of the second law, but it's a consequence of the third law. So that's the reason why the third law is usually accepted as being a separate postulate, which is independent of the second law. Obviously, everything is intertwined, and there is overlap, but this is the idea. Okay. One more, the most important thing though, and I already discussed, is that the third law points to the fact that most of the models that we have are not compatible with a zero entropy at 0 Kelvin. And in order to have them, that means that the models are simply wrong. They were not built to account for observation at extremely low temperatures, simply because experimentally they were not attainable. So they were actually built from a heuristics usually at usual temperature. So that leads us to the summary of this last lecture on the thermodynamic part, and next lectures will be on the statistical physics. And then we've seen the third law, which which basically are all equivalent. From Nernst said that the entropy no longer changes when and it was an experimental observation that the entropy no longer changes at low temperature. Planck said that the entropy of system at in equilibrium, in internal equilibrium, is actually zero, and it may be taken to be zero. So it actually sorry, what it means, it is at 0 Kelvin, the entropy is zero, while in fact it is constant, and that constant is the same, so we could choose the constant to be zero. Simon was the definition is actually more satisfactory from a perspective of keeping the physics, the unknown in physics, clearly on the radar screen, is that the contribution of the entropy of a system by each aspect of the system, which is in internal thermodynamic equilibrium, tend to zero. So we know that each of them separately tend to zero, and that we can do separately because the logarithm of the number of microstate ends up being the logarithm of the sum of each contribution. The sum of the logarithm of each contribution, sorry. We also saw that temperature equals zero cannot be attained in a finite number of steps, and the third law implies that heat capacity and thermal expansivity tend to zero at the low temperature as well. We also, the fact that the entropy has to go to zero at 0 Kelvin shows that the Curie's law is incorrect, and in fact it's terribly incorrect, because Curie's law predict the minus infinite entropy essentially at 0 Kelvin, even though the entropy is zero. So that's pretty bad. Okay, so thank you very much for your attention, and I hope you enjoyed all those lectures so far, and please come back for more.